Great, it's recording now. Today we're going to talk about section 4.5, derivatives and the shape of a graph. Gonja, welcome. We just started. Hello. Great. So we are going to talk about how the derivatives, first derivatives and second derivatives are related to the shape of a graph. Okay, so let's start with what mathematicians call the first derivative test. This test tells us the relationship between the derivative as a rate of change, instantaneous rate of change to be precise, and the shape of the graph. Mathematicians figure out three scenarios. The first scenario says that if your derivative, when computed over an interval, open interval to be precise, one more student joining, great, is positive somehow, right? So if you figure out and show that your derivative over some open interval is positive, it means that your function from left to right is increasing, okay? Increasing, derivative positive. Now let's say you reach this peak, this top of a mountain, and then at that point, your curve becomes stationary, right? And since the function is differentiable here, derivative has to be zero, since the function is smooth, right? But then right after, if you continue walking along this curve from left to right, notice you are going down. The output values are decreasing. So this just means derivative-wise that the derivative has to be less than zero, okay? So from left to right again, increasing, derivative positive, you reach a stationary point, derivative zero, you continue walking, the trend changes, decreasing, negative derivative, okay? And this is what in the theorem mathematicians call the input value C. See here. Now, if you're going from increasing to decreasing, then you got yourself what is called a local max, right? It's what separates increasing from decreasing, going from left to right. First scenario. The second scenario says that if you walk along your curve again, you trace your curve from left to right, and somehow you are going down now, the output values are decreasing. So this should be associated with the derivative being less than zero, okay? Decreasing. You reach this stationary point, this bottom of a valley here, the floor valley, let's call it. Here, derivative zero, since the function is differentiable, right? Now, if you continue walking from left to right, now increasing should be associated with derivative greater than zero, okay? And this point is what the mathematicians call the point C, right there in the theorem, formally speaking. This is scenario two, right? Scenario two. There is a third scenario, which is not so often presented on the exercises, but it's possible that you may encounter these tricky scenarios. Look, if you start walking from left to right again, going up, right? Increasing. So this should be associated with derivative greater than zero, right? You reach this weird point, right? Because I cannot say that this point, yeah, but before, let me write here local minimum, this one, right? Local minimum, yeah, local minimum for this, because it's what separates decreasing from increasing, right? Local minimum here. Yeah, but then let's talk about this special case, right? Increasing first, then you reach this special point. It's like a hybrid point there, right? It's not really minimum. It's not a maximum, right? Neither minimum nor maximum, right? It's just a stationary point, right? Where kind of the curvature changes, right? Then whenever you encounter this type of point, you just continue walking, and then you get to see that increasing here, but it's still increasing here, right? In a different way, though, right? In a different way. So this is still increasing, it's still derivative greater than zero. Now, at this weird point, though, if you draw that tangent line, notice that it's still horizontal, right? Compared with these tangent lines. So it's still, the first derivative is zero, right? But be careful here, right? we cannot say that this is a maximum locally speaking or a minimum locally speaking, right? We have to say this point. I'm gonna put an arrow here. This point is neither a local max, nor a local mean, right? It's like a hybrid point. And if you want to know what kind of point is this, I can tell you in advance, because this is gonna be seen later today, but later. This is what mathematicians call an inflection point, because the curvature is changing, right? It's increasing, but the curvature is changing. So in advance, this inflection point. And we will require the second derivative to catch them, right? Inflection point. All right, so just be careful with this, right? Derivative equal to 0, 98% of the time, it will either be associated to local maximum, local minimum, right? But it could be that the derivative equal to 0 could be associated to these special points, which we're going to call inflection points, right? So be careful there. But of course, it helps tremendously to know that the derivative is 0, right? To get these local maximum, local minimums. Because as soon as we see change on the trend, then it means that we got yourself a local extremum, right? Either local maximum, local minimum. But if there is no change of trend, right? Here, increasing, still increasing, or it could be decreasing and still decreasing. Then we kind of reserve our judgment there, right? Yeah. This is called the first derivative test, right? The sign of the derivatives would tell us if the function is increasing or if the function is decreasing. All right, so now here in our textbook, they have summarized here these ideas to give us like a strategy to deal with this localization, or to deal with when the function is increasing and decreasing, and if we're dealing with a local maximum, local minimum. Here are the steps, right? The strategy is first, if you are giving a graph, and you are asked to identify local minimum, local maximum, first, get all the critical points. Get a derivative, set it equal to 0, find your critical points. Next, analyze if the derivative has a positive sign or negative sign. According to that, you will discover that your function is either increasing or decreasing. And step 3, the last step, when you catch a change on the trend, right? Derivative positive to derivative negative, or derivative negative, and right after this stationary point, derivative positive. Then you got yourself a local extreme, right? Either local maximum, local mean. But if somehow the function has a derivative that does not change its sign, right? It stays positive all the time or it stays negative all the time, then you just reserve judgment. Later, I will tell you what to do with this situation. All right, guys, practice now, example, right? Concrete example for you to see how this works. Using the first derivative test to find a local extrema, either local maximum or local minimum. Well, first, you have to take the derivative, because the derivative is going to tell us where the critical points are, right? So let's start by taking the derivative of this function. It's going to be 3 x squared minus 2 times 3, 6, x minus derivative of 9x is just 9. Good, this is our derivative. Now, next I have to set my derivative equal to 0 in order to find the critical points, right? The critical points. The input values such that the derivative is 0, right? So we are working a polynomial function, right? That's why I'm saying that. So now we can factor, right? Yeah, Gonja already, yeah, we are headed there. Gonja, excellent, excellent, right? Now factor out 3, for example. If you do that, 3 into 3, 1, 3 into 6, 2, 2x, minus 3 into 9, 3, right? This is the factorization, equal to 0. If you factor further this part, after some trial and error, you will see that this is x, this is x. Two numbers whose multiplication is -3, whose sum -2, are -3 and 1, right? -3 and 1. Great, 0. From there, set each of these guys equal to 0. You may say, what about the number 3, Professor? Number 3 doesn't matter because once you divide both sides by 3, it disappears, right? Disappears. So yes, these guys. X minus 3 equal to 0. And x plus 1 equal to 0. From there, we will get your critical points, right? 3 and minus 1, right? Very good, very good. Now, conclusion, right? So -1 and 3 are critical points. This is the first step. Find your critical points. We are dealing with a polynomial function for the derivative, so we don't need to look for places where the derivative doesn't exist, right? These are all the critical points. Step 2 is set your critical points on a number line, okay? So you draw a number line, the best you can here. And then there, you're gonna set your derivative, right? Not the critical points, critical points. And what you're gonna do with the derivative is you're gonna collect here the signs of the derivative of f prime, okay? So the critical points are in order, right? -1 is somewhere on the left of 0, and then 3. Set them somewhere there, 3 here, right? Now, these critical points, when you put them on the number line, right here, -infinity, here infinity, they are going to separate your number line or partition your number line, right, into sub-intervals, right? This one sub-interval, another one here at the center, and another one here, right? 3 sub-intervals. Now, you must figure out what is the sign of your derivative over these 3 intervals, right? For that, guys, this is the method. We are going to use a test point for each region. I am going to start here on the rightmost region. I'm going to try to figure out what is the sign of the derivative here. Let's take a test point. Let's say I take as my test point 4, test point 4, okay? I am going to evaluate my derivative function at 4 and see if it is positive or negative. Look, this is my derivative, right? Let's evaluate our derivative at 4. Well, then you can use the calculator in case the numbers are not friendly, or you can do it in your mind, okay? But I'm going to use the calculator so that if you're doing homework and the numbers are not friendly, you can follow this. -6 times 4 minus 9. I get 15. 15 is positive, right? 15 is a positive number. So let's write it out. 15 here, positive. Positive, greater than 0. So it turns out then all this region will have positive derivative. It's a property of this type of functions, okay? So you just have to check with a test point if the derivative is positive or negative, and the sign will be the sign of the derivative for the whole region, for the whole sub-interval. Yeah, very good, the calculation, right? Excellent. Yeah, so here, positive derivative. Now I need to find out what is the sign of the derivative here. Let's use a different color. For that, I'm gonna take a test point. What do you think would be a good test point, an easy test point to consider here between negative
0.
There you go, guys. Yeah, I see you are too. 0, right? Yeah, it's not like we are lazy, right? You know, it's just that you want to work efficiently, right? Efficiently. 0 is super easy to evaluate. Look, you 0 evaluated here is 0, 0, -9, right? So quickly, negative, right? Negative. So it means that all this sub-region is negative, okay? The last region now, let's use a different color. For this one, let's use orange. We gotta take a test point here. -1, I'm gonna take -2 as my test point, okay? So f prime at -2. When you do the computation here, yeah, someone already, I have 15, right? 15, yeah, if you do that, 15 is what you get. And you can try with your calculator or the Desmos calculator. Este evaluation is 15, it's positive. And it means that all this region, right? Positive, derivative. Great. So now then I can say, right, that over this interval, the function will be increasing, right? Increasing. And why you say that, Professor? Because the derivative is positive, increasing. Over this region, the green region or subinterval, decreasing, right? Decreasing. Because the derivative is negative, decreasing. Over this red region or red subinterval, again increasing, right? Increasing. Because the derivative positive, right? So this kind of gives you an idea of what the shape of this graph should be, right? Increasing, then decreasing, increasing, right? So you can even attempt to get in general more or less what the shape should be, right? Look, this is saying the function is increasing, here derivative 0, critical point, right? Then decreasing, decreasing, and derivative 0, critical point, and then increasing again, something like this, right? Chair-like, right? Chair-like makes sense because it's a cubic function, right? Look like a chair. All right, so now let's pick up the local extremum, right? So let's write here conclusion. Following the first derivative test, right? If I go from increasing to decreasing, I get myself a local max, right? Local max here, local max, local max. Yeah, so let's write here, local maximum at x equal -1, right? At this point, a local maximum. But moreover, I can say what is the value of the local maximum as an output value, right? You can say what is this value. How you do that, Professor? Well, I just evaluate the function, the original function though, right? This one at -1. Let's do that together. So let's use now the original function, the original function, no longer the derivative, right? This one. And let's evaluate this at that particular value, -1, right? Square. Yeah, and you may say, Professor, I can do this in my mind. True, but in case it's not 1, let's say 3, 4, 5, and you need in your homework help, use this, right? This is how you compute it. It's a 4, right? A 4. It means that the partner of -1 via this function is just 4, right? 4. So this is going to be the actual value, the actual maximum value, locally speaking, right? Locally speaking. And sometimes mathematicians put this together by saying, this is a local maximum, this point, -1, 4, right? 4, this guy. Great. Now you continue walking from left to right. You see there is a change of trend, right? Which justifies this local maximum, right? But then when you reach this point here, the lowest locally here around the input value 3 in the neighborhood of 3, right? This is clearly a local mean, right? Local mean. Now it's a local mean and happens at x equal 3, right? So we can write local minimum at x equal 3. But not only that, I can actually find the value of this local minimum. How can I do that, Professor? Well, I can just evaluate this at 3, right? And I will get something. That something will be the value, the local minimum, right? It happens at x equal 3, but it has a value. What is that value? Now you go and work with the original function, right? Original function. So this one, a little bit hard if you compute it probably in your mind, but you can always use your scientific calculator there. There you go, -9 times 3 and -1. I got -28, right? -28, look here below, right? Very good. So -28. Very good. So this is telling me that the actual minimum value, locally speaking, around this input value 3 is -28. Mathematicians put these two together by saying that there is a local minimum having these coordinates 3 comma negative 28, right? That's it, which is this other point right here. Great. You follow, guys? So this derivative allows us to say where the function is increasing and where is decreasing, but not only that, looking at the separation, what separates increasing from decreasing, local maximum. Looking at the separation of decreasing and increasing, local minimum, right? This function does not have absolute maximum because it grows forever here in this direction, does not have absolute minimum because it decreases forever in this direction, right? But local max and local min were found. All right, guys. So now I want you to do this, what I did here, yourself here. Try. When you deal with a parabola, it's very straightforward. So we're not going to do the parabola, but we're going to do this one, the cubic function. So can you try this one? And as a hint, I will give you some steps. Hint. Find first the critical points. First, find critical points, right? By setting the derivative, in this case, let's be formal, is y the function. So y prime, by setting y prime equal to 0, right? And solving for x. Yeah, get the critical points first. Then we will go over the number line, right? We will put them there. Then using test points, we will figure out where the derivative is positive, increasing, where the derivative is negative, decreasing, right? Yeah. And finally, looking at the separation between increasing, decreasing, in which order they happen, then we will get the local max and the local mean. Yeah. Yeah, if you found the critical points, let us know. So to see if you're in the right track. Two. Yeah, number 2. Let me see. Yeah, it's very tricky, this function. I think one of them is correct, but the other, yeah, let's see. Yeah, let's do it together and I can give you maybe the next, right? Or something else. So let's see. First derivative, yeah, critical points. You got it right, the critical points. Very good, excellent, yeah. Yeah, Miguel also one good, but the other one is not, okay. But I will explain, it's a tricky question. Okay, first step, you get the derivative, right? Remember the derivative is the hero of calculus, right? Whatever you do, 98% of the time you will use the derivative. So derivative here, 3x squared minus 3 times 2 is 6, right? The 2 coming down, derivative of this 0. This is the derivative. Now, we are supposed to set our derivative equal to 0, right? Set y prime equal to 0 and solve for x, right? Solve, let's write these steps here, for x. So you can kind of remember this. Okay. So 3x squared minus 6x equals 0. And here comes the tricky part. When you factor this guy, the greatest common factor happens to be 3 for 3 and 6, right? For x squared and x, you always take the one with the smallest exponent, which is x raised to the first power, right? So this outside, the greatest common factor. Now 3x into 3x squared, 3 into 3, 1, x into x squared, x, minus, 3x into 6x, 3 into 6, 2, x into x, they cancel, right? Just 1. So this is the result of factoring, right? Good. So now this is equal to 0. And now we are supposed to set each factor containing a variable equal to 0, right? There is a number 3 here. Don't worry about that, because once you divide by 3 both sides, disappears. So x times x minus 2 equals 0. And here is probably the tricky part. X is alone here, so just set this equal to 0. And then x minus 2 equal to 0. So here I have a critical point, right? But here I have another critical point. So x equal to, right? So 0 and 2 are the critical points, right? The critical points. Next, you are going to set these critical points on a number line, right? A number line. I'm going to insert a number line here. And this is what we're going to do. This is bring our number line down here. Yeah. Great. I see someone.
For the number line,
excellent. Yeah, for the number line. Excellent. Yeah, very good. Yes, that's the sequence, the right sequence, right? So we're gonna put 0 in the middle, right, of the number line 0, and the other one is 2 on the right here, 2. This 0 and this 2, they subdivide, they partition our number line into 1, 2, 3 sub-intervals, right, or regions. And that goal is to figure out the sign of f prime over these 3 regions, right? These 3. Now, in this case, the function is called y, so allow me to write this y prime there. Great. I always start here at the end, at the rightmost, but you can start anywhere. Here I have to choose a critical, a test point, right? Test point. Next, on the right of my critical point. For convenience, out of convenience, I'm going to choose the number 3, okay? I'm going to see what is the derivative at 3, if positive or if negative. So you go here to your derivative function, right, which is this, and then you figure that out, right? You can do it with a calculator. Very good, excellent, right? I just do it for everybody to see. So if you plug into the derivative, right, which is this guy, right, 3x squared, 3 squared minus 6 times 3. What I get is 9, right? Very good, math. 9, positive, right? Positive. That's what really matters. Positive 9, yeah, 9 positive, greater than 0, right? So it means that all this region is going to have positive derivative. So increasing, right? Yeah, sort of in advance. Now, between 0 and 2, let's choose another critical point. No critical point, test point, right? Test point. Between 0 and 2, out of convenience, I'm going to choose 1 as my test point. So now I have to evaluate my test point at the derivative, which is here, right? Let's do it in our minds. Look, 1 squared, 1 times 3, 3. 6 times 1, 6. So 3 minus 6, minus 3, right? Minus 3. So negative, right? Yeah, great. So this one negative. Someone wrote something on the chat. Let me see. Negative, right? Excellent, math. Yeah, negative 3, right? Yeah, now we get to this region, right? The third part. Let's choose another color here. Let's choose orange. For this part, I'm going to take as my test point -1. You can take any test point as long as you are on the right left side of 0, right? I could have taken -2 just to make it easy, -1. Look, -1 squared is 1 times 3, 3. -1 times -6, positive 6. 6 plus 3, 9, right? 9. So 9, which turns out to be a positive number, positive. Very good, very good. We have the whole distribution sign-wise of the derivative, right? Where is positive, where is negative. Great, great. Excellent. And sometimes when I do this a lot, the students ask me, Professor, will they always switch the signs? And answer for that question, guys, most of the time, 90% of the time, I would say, but not always. Not all. There are some special functions that I will show later, next, where the signs get repeated. It's possible, okay? So just be careful with the test points. To play safe, use test points, because not always they will switch. All right, but now, as I did before, right? Now at this point, I know that the function is increasing here, right? Positive derivative. So I can kind of guess its shape, right? The shape of its graph, increasing here, right? Increasing, and then reaches this point, derivative 0, right? Then decreasing, right? Until it reaches this point, derivative 0 here, right? Let's do it nicely so that we don't come out. Yeah, so derivative here was 0, negative. Yeah, so decreasing here, right? Decreasing. Yeah, I hear someone writing something on the chat, right? And then up to here, and then like this, right? Increasing again after 2, right? Yeah, very good. Great. Yeah, so now then it's time to identify. Aha, Ma, now you figure it out. Yeah, excellent, excellent. Yeah, you got it. Yeah, you got it. Yeah, excellent, excellent. Yeah, so now I know that it's increasing here, decreasing here, increasing here again. Clearly, this should be a local max, right? This one should be a local mean, right? Local mean, because it goes from decreasing to increasing. And then further, I can say, right, local max happens at 0, right? At 0, but this 0 has a partner through the function, right? Here, look. If you evaluate y at 0, it's possible to find the partner, the other coordinate that corresponds to x equals 0, right? It's an easy computation, right? With 0, 0 disappears here, 1. So believe it or not, guys, 0, 1 should be the coordinates of the local maximum. Now for the local minimum, look, local minimum happens or occurs at x equal 2. But then it's possible to find the partner of 2 using the function, right? Now we just evaluate 2 into this function. I'm gonna get 2 cubed minus 3 times 2 squared plus 1, right? 2 cubed is 8. This is 4 times 3, 12. 8 minus 12 minus 4 plus 1 minus 4 plus 1 minus 3, right? Now, if you prefer to type it in the calculator I showed before, right? For the sake of variety, I'm doing this just mentally now. So this minus 3. So there you have your 2 critical points, right? So you go back here and you realize that this is the one, right? Local maximum at 0,1, local minimum at 2, minus 3. Very good. Okay, guys, now let's see some special cases, right? We've seen that here we've been working with polynomials. It's pretty straightforward, right? You just follow this strategy, you should be fine. This is a cubic polynomial. You should do it at home. But let's see what happens when you pick something, a function, for example, that is not a polynomial function. For example, this rational function. Let's see what happens, right? Let me show you this and I will ask you to do another one. So if they give you something like this, well, then you should follow the method, right? The method says, okay, first you have to start by taking the derivative, right? But before doing that, I'm going to rewrite my function as follows: x squared plus 1 raised to minus 1. So I can easily take the derivative using the chain rule. Look, using the chain rule, notice the outside function is this. The inside function is this x squared plus 1, right? Good. So taking the derivative of the outside function, that's going to give you negative 1 here times here x squared plus 1 raised to minus 1 minus 2, right? Simplifying this, notice the derivative will end up being this: minus 1 on the top. This guy can be written in the bottom, right? Like this, right? X squared plus 1. This is the derivative, okay? Great. Now, the next step is to set that derivative equal to 0, right? Equal to 0. But don't forget that here, after I take the derivative of the outside function, you have to multiply it by the derivative of the inside function. Derivative of x squared plus 1 is just twice x, right? Twice x. Multiplying, we get finally this as our derivative, x squared plus 1. Very good, very good. So now, don't forget also the exponent. I think I forgot this here. This is 2, right? Negative 2 becomes 2. So this is the final version of my derivative, yeah. Right? Now let's continue here, right? The next step is to set my derivative equal to 0, right? Equal to 0, and see how I can get some critical points. So set derivative equal to 0. And let's see if we can catch some values of x such that the derivative is 0 and get some critical points. Setting my derivative equal to 0, dividing both sides by -1, multiplying both sides of the equation by this amount, which is never 0, so we are safe there. We will get the following. We will get that this guy leads to, as a solution, the following. I will write here. It leads as a solution the following. Again, let me just multiply here both sides by x squared plus 1 squared. This cancels this, minus 2x equal, this multiplication is 0, right? And dividing by -2 both sides, I get that x equals 0, right? This is a critical point. But now, guys, remember, if you are not dealing with a polynomial function for your derivative, you have to be careful. Perhaps there will be more critical values associated to this derivative being undefined. But since God here, notice the denominator is x squared plus 1, right? This x squared plus 1 is never 0. Here is the reason. If you add 1 to both sides of this inequality, x squared plus 1 is greater or equal than 1. Never 0, right? Never 0. So we are safe here, right? So this is the only critical point, 0, right? Yeah, critical point, 0. Great. With that critical point, then we're going to go to the number line, right? Remember the number line here? Here, negative infinity, here infinity. X equals 0 should be placed in the middle, right? In the middle. This critical point is going to separate the number line, split the number line in 2 parts, right? 2 regions, right? And now our goal is to find the sign of the derivative of this function, sign of y prime over this region, okay? For that, I'm going to take test points, right? What should be a good test point for this part? Anyone could tell me? Someone wrote something in the chat.
1.
Yeah. Very good. 1. Yeah, very good. Very good, Deep. Very good. I think you got it. Yeah. 1 would be a good test point, right? You could take 2, 3, but you know, try to pick something that is easy to evaluate, right? So now evaluate your derivative at 1. My derivative is here, right? I got it here using the chain rule. So this evaluated at 1 will be, this is 1, this will be 2, 1 squared 1, 1 plus 1, 2, 2 squared 4, 2 over 4, simplify 1/2, right? 1/2, negative 1/2. So negative 1/2. Feel free to use the calculator, guys, in case you can not do it mentally, right? But it's negative 1/2, negative. So this means that this whole region, negative derivative. Now let's look at the right region, the right subinterval. Anyone could give me a good test point for this part?
-1.
-1, excellent. Gonja, -1, right? Yeah, try to be efficient, right? There's no reason to take 10, 20, because we want to just do the computations quickly, right? So -1, very good test point, because look, this will be -1 times -2, +2, right? +2. -1 squared is 1, 1 plus 1, 2, 2 squared 4. So I get 2 over 4, 1/2, right? Positive, positive, 1/2. Excellent. So this positive, right? Positive. Yeah, again, they switch, right? But now notice it's starting with negative, positive. There are kind of combinations, right? The switch of signs is very common. I would say 90% of the time, but there are some times, some exercises they will repeat. Probably we will see one of them next. All right, next, then you say, okay, positive derivative means that the function increases, right? Increases. So you can draw something like this, increasing, until it reaches this special stationary point, right? Derivative 0. So it has to, the trend has to change. Now decreasing, right? Decreasing, something like that. It will look something like that, right? Yeah, so now we can say that we got ourselves then a local max, right? A local max, clearly. This point is a maximum in the neighborhood of 0, right? So local max. So we can say, local max 0,0. But at the same time, since this local max is the highest output value on the overall, look at the overall of the function, right? This goes down here, this goes down here. This is the highest of all possible local maximum. So then they call it an absolute maximum, right? Absolute max, right? It's also a local, it's an absolute maximum. If you look at this globally, if you look at this locally, around 0 is a local maximum, right? So this would be 0, comma, 0 has a partner, right? When you substitute 0 into the original function, this one, you will get 1 over 0 squared plus 1, this is 0. 1 over 1 is just 1, right? So partner of 0 via the function 1. So 0, 1 should be the absolute maximum, right? So the absolute maximum occurs, happens at 0, but its actual maximum value is 1, right? So absolute maximum is 1 at x equals 0. Yeah, very good, excellent. Yeah, great.
How was
Go ahead.
This is Gonja. How was the value is 1? Can you please explain that again?
Oh, how, what was that? Sorry, how we got the
value is 1. Value is 1.
Oh, how we got this value 1? How?
Yeah. Yeah.
Yeah. Okay. All right. Notice the 0 was here, right? The 0.
Yeah.
Yeah. The 0 was there. But this this graph is the graph of the function. This function, right? Y equal 1 over x squared plus 1. So what I did, I evaluated this function at x equals 0. This function.
Oh, okay. Okay. Got
yeah.
it.
And then this disappeared 1 over 1, 1, right? Yeah. Yeah. Evaluation. Just the evaluation of the at the original function, though, right? It has they confuse the derivative. It has to be evaluated at this point, right? Yeah. This is this evaluation, right? Yeah. Mm-hmm. Yep. Very good. Very good. Good question. Yeah. Always, guys, clarify if something is not clear. Don't hold it back. Just let me know. Okay. Very good. Yeah. So as you can see, right, this was kind of a little bit different than the examples before. Maybe we can try something else, another special case I will show you. Okay, I will ask you to try first and see if you can figure it out. It's very tricky. This one, yeah, yeah, yeah. Let's go over this and then let's move on. Yeah, I'm gonna show you this and I'm gonna ask you to do number 8, right? Because they're very similar. But let me show you. This is a very extremely tricky case. Suppose they ask you to figure out the critical, not the critical point, the local maximum, local minimum in this for this function, x cubed minus 3x squared plus x minus 8. All right, and you follow the method, right, that I gave you, which is take the derivative first. The derivative is 3x squared minus 6x plus 6, right? And then you set your derivative equal to 0, right? Yeah. So 3x squared minus 6x plus 6 equals 0. But now, once you factor 3 out, you will realize that this part inside, 3 into 3x squared is x squared minus 3 into 6x, 2x, plus 3 into 6, 2. You will realize after you remove this 3 from the scene, right, by dividing both sides of this equation by 3, that this guy is not factorable. It's not. You try to look to numbers that when multiplied, they give you 2. When added, they give you -2. impossible to find those numbers, right? You may say 1 times 2, Professor. Yeah, 1 times 2, 2. But when you add 1 plus 2, that's going to be 3. Or even if you change the sign, -1 plus -2, -3. Not factorable, right? Now you may say, okay, Professor, but we have the quadratic formula. Yeah, even if you use the quadratic formula, it's not factorable. Yes. Let's say you want to double check, right? That this is not factorable, no factorable. Using quadratic formula, with 1 here, invisible 1, right? With A equal 1, B equal -2, and C equal 2. Look what's going to happen. X is minus B plus minus B plus minus the square root of B squared minus 4AC over twice A, right? This is what the quadratic formula tells us to find a solution. So if we plug into the quadratic formula the values that we have, B is -2, the square root of -2 is squared minus 4 times A is 1, C is 2. Look what happens there, twice A, twice 1, right? X equal, minus and minus is plus, so 2 plus minus. Here inside the radical, we're gonna have trouble. -2 squared is 4. This is 8. 4 minus 8, minus 4. Square root of a negative number there, right? Negative number. So this is not a real number, right? Not a real number. It's a complex number, right? But not a real number. This graph, they deal with real numbers, not with complex numbers. So whenever you encounter this, then you have to say, conclusion, no solutions, right? For these equations. No way to get the derivative to be 0. The derivative is never 0. So no critical points, right? No critical points. No critical points. Right? So if there are no critical points, there are no stationary points, right? No stationary points. So which means that the graph either goes up forever, right? Or decreases forever, right? But no critical points. So if this is the conclusion, guys, which choice do you think I should pick here? Anybody? Which choice? A, B, or C? Look at the choice.
C.
C.
C. Excellent, guys. Yeah, I think you got it, right? The function will grow up forever or decrease forever. It's not going to have any critical points, any local extremum, any local minimum, nor local maximum, right? So you go for none, okay? Yeah.
Professor, can you show this graph on the decimals?
Oh,
graph?
absolutely. Yeah, yes. Yeah, thank you, Ma, for bringing this up. Look, you guys have these tools, right? Let's say this looks weird, right? I want to make sure that what I'm doing is right. Maybe I just couldn't factor it, you know. I want to double check, graph it. Look, when you graph it, you will see this, -8. You see, this graph looks like a snake or like a chair-like, but it's a special chair. It's a chair where you cannot really sit, right? Look, there is a change of curvature, which later we will call inflection point, but it's not really that the derivative is 0 here, right? It just keeps growing. Maybe I can make it bigger, the graph. Look at the graph. Always increases, right? Increasing always. So it means that doesn't have any stationary points. So no local minimum, no local maximum, right? You follow, guys? Yeah. Always increasing, right? Always increasing. Never decreases this function from left to right, of course, right? Yeah, very good. Excellent, excellent, Matt. Whenever something doesn't look familiar, graph it and check, right? Check that you are in the right place. Very good, very good. Yeah, excellent. Yeah, when you graph these others, right, you will see this bouncing, right? Like when you graph this confirm always, right, you will see something like that, right? The scale, of course, may be different, but I'm just showing, right, how the shape should be, right? Great. Now, can you try this one? Number 8 is similar, and then we will move on to talk about curvature, okay? Curvature, okay. Well, we will spend some time. Try to do this just to make sure that you will not be in trouble on the homework. So I will leave this there for you to have as a reference, okay? Yeah. Try this. Remember the hint, take the derivative and set it equal to 0 and see if you can find critical points, right? If not, you know what to do. Yeah, I'm gonna write here as a hint, set y prime equal to 0, right? And then solve for x and see if you can solve for it. If not, you know what to do. Yeah, and then we have to talk about concavity. Yeah. All right, guys, let's do it together so we can take the first break, and then later we will talk about concavity. Someone figure this out. Deep. Yeah, you made my day. Yeah, you figured this out, right? Correct. Very good, very good. Yeah, so you follow the guidelines, right? The guideline says, okay, derivative equal to 3x squared. More students are posting answers. Yeah, very good, very good. Yeah, very good, Gonja, very good, very good. Yeah, Miguel also figured it out. Yeah, great, guys. Very good. Yeah, so let's do it together, right? 3x squared, the derivative, minus 2 times 3, 6x, plus derivative of 5x, 5, right? And let's set our derivative equal to 0 to see if we can find some values of x such that the derivative is equal to 0. Notice I cannot factor out 3 this time because 3 doesn't go into 5, right? So I just basically go ahead and use the quadratic formula, right? To see if this has a solution or not, this equation, right? So A equal 3, B equal -6, C equals 5 will be considered for the quadratic formula. Minus B plus minus square root of B squared minus 4AC all over twice A. If we apply our quadratic formula, I have to do this. Minus B is -6 there, plus and minus the square root of B minus 6 squared minus 4 AC. A is 3, C is 5. Divided by twice A, twice 3, right? Simplifying this, I'm going to do it here. X will be equal to 6 plus minus this inside. Look, -6 squared is 36. Since the number are not that friendly, let me just do it in a calculator, right? 6 squared minus 4 times 3 times 5. Negative number, right? -24. So it means that we got ourselves in trouble because we're working with real numbers for this graphing, right? So this is not a real number. This is not a real number because the inside of the radical is negative, right? This is not a real number. So which means that this function does not have critical points, right? Conclusion, no critical points. No critical points. So therefore, we will never find a stationary point, right? Tops of mountains or the bottom of a valley, we will never find those kind of points, right? So it means that this does not have critical points, and therefore neither absolute maximum, neither absolute minimum, right? Nothing, so you go for none. Follow, guys? None, right? And as Ma suggested, right, if you're still not convinced, right, that this is the case, graph it, and you will see that the derivative will never be zero, right? And it will either be always increasing or always decreasing. Okay, but no critical points, so therefore no local maximum, no local minimum, no absolute maximum, no absolute minimum, right? So it looks like a chair, where you cannot sit down to rest, right? Look, this is called an inflection point. All right, later we will talk about that in details. Okay, guys, so teachers figure out that the derivative controls the trend, right? When the function is increasing and when the function is decreasing, right? Positive derivative, function increasing, negative derivative, function decreasing. But there is one thing, right? Let's say when a function is increasing, there are two ways for the function to increase, really. Two ways, Professor, what do you mean? Well, for example, right, if you, let's just put it on the side, okay? This function is increasing, right? But it's increasing curving up, right? Curving up, increasing, curving up. But there is another way to increase, increasing curving down, increasing curving down, right? Wow, Professor, what curving up, curving down? For you to see, it's kind of based on a real world analogy. Imagine you're driving a car, okay? And you are moving forward, but you are accelerating here, accelerating and moving forward, right? Sorry, this would be the case. Accelerating, moving forward. This one, decelerating, sorry, but moving forward, right? Decelerating, moving forward. Decelerating, moving forward. But that's not the only way to move forward. You could be accelerating, right? Accelerating, moving forward, right? Two ways. So even though you discover that the function is increasing, you can go deeper and see if it is increasing curving down or curving up, right? This is curving down, curving up. Let's fix it. Yeah, this is opposite. Curving up, curving down here. Yeah, curving up here. Okay. Let's be careful there. Yeah. Very good. Curving up. Accelerating, moving forward, decelerating, moving forward, right? So this is then when mathematicians figure out that the second derivative is what controls this, right? If it's curving down or curving up, the second derivative. For that, they discover that if the second derivative is positive, it will curve up. It will curve up here, right? The second derivative positive, curving up. And this can be easily remembered by imagining a happy face, the shape of the mouth of a happy face. And mathematicians call it formally concave up, right? Curving up. Now, for this situation, when the second derivative is negative, then if the second derivative is negative, then it curves down, right? Curves down. Then they associate this with a frown face. The mouth of the frown face is concave down, concave down. So concave up, concave down. Now, another way to easily remember concave up from concave down, when it rains, concave up contains the water. When it rains, concave down spills water. Maybe we can write it, right? When it rains, imagine drops here. Notice concave up holds water, right? Holds water. So when it rains, concave up holds water. When it rains, concave down, it spills the water, okay? So the water is not gonna be contained, it will spill. Yeah, so here, when it rains, concave down, spills water. All right, so this is another way to differentiate concave from concave down. A third way, when you graph the curve, if the dominant is the curve with respect to the tangent line, it means that the curve is concave up at this point, because curve above tangent line, right? Concave up. If when you draw the tangent line at one point, the dominant is the line, right? And the curve is below. If the curve is below the tangent line, then this is concave down, right? Concave down. Okay, so these three ways will help you to identify when it's concave up, when it's concave down. The formal definition of concavity is this: let f be a function that is differentiable over an open interval I. If its derivative is increasing over I, we say that f is concave up. If the derivative is increasing, right? Not the function, but now the derivative. And if the derivative of the function is decreasing, then we will call it concave down, right? Derivative increasing is like accelerating the car when driving, right? Derivative decreasing is like decelerating the car when driving, right? Kind of like that. Now, there are 4 possible scenarios for concavity, and these are the 4, right? This one, increasing concave up, moving forward, you're accelerating. Here, moving forward, decelerating, concave down, right? There are 2 more here. Let's say you're driving backwards, no forward, but accelerating, going backwards, this is what you get. You're moving backwards, but decelerating, this is what you get, right? Concave down. Yeah, so this is how this works, right? Yeah, here the first derivative increasing. Here, first derivative also increasing, but in a negative sense, right? Very tricky. Here, the first derivative decreasing, right? Here, the first derivative also decreasing in a negative sense, right? Great. Now, before we go to the test for concavity, I want to just make sure that everybody understands what this idea of concave up, concave down when you have to look at graphs, right? But this is what you're going to do. So let's say they give you these graphs and they tell you, right, over which intervals is this function concave up, over which intervals is this function concave down. I'm going to show you how to do number 1, and I will ask you to do number 2, okay? So use the graph of the function to locate the local extrema and identify the interval where the function is concave up and concave down. Well, as usual, we travel along the function from left to right, okay? And here, look, you go up here, then we reach up top of a mountain, then we come back, right? This resembles the mouth of a frown face, right? Mouth of a frown face. So it means that we are dealing with part of the curve that is concave down, right? Concave down. But where? Over which interval? Here is negative infinity, right? From negative infinity up to 0, right? Up to 0. So you say on negative infinity up to 0. Now, if you continue walking from left to right along the curve, here, look, what does this resemble? Resemble the mouth of a happy face, right? So it means that we're dealing with concave up, right? Concave up. And where? On from 0, right? 0 is here at the origin, right? All the way up to positive infinity or just infinity, right? From 0 to infinity. But now, in addition to that, they want us to identify these special points, right? The relative maximum, relative minimum. Well, here, clearly, since it's changing from increasing to decreasing, relative maximum or local maximum, right? And here, let's use a different color. Here, local minimum, right? Because in the neighborhood is the lowest output value in the neighborhood, 1, here in the neighborhood of -1. So combining all this, we can say that the answer should be this, right? Local maximum at x equal, sorry, I have to, at -1, local maximum, so local minimum, sorry, that's correct, right? Local minimum here at x equal 1, local maximum at x equal -1 here, right? Concave up on 0, infinity, concave up on 0, infinity from here to here, right? As we stated, and concave down on -infinity to 0, right? You follow, guys? Yeah, that's that. All right, so try to do this on your own. Could you figure this out? Number 2, identify where the curve is concave down, where is concave up, and together with that, identify the location of the local maximum and the local minimum, right? And here you don't need computations, guys. Just trace the graph from left to right. If it resembles the mouth of a frown face, concave down. Resembles the mouth of a happy face, concave up. Right? Concave up.
Is it B?
Close, very close. But local minimum at x equal 3, local max, local minimum at x equal 3, correct. Local maximum at x equal -3. But the concavity, look, concave down on -infinity, -3. Yeah, the concavity, check the concavity. It's very, very close to the answer. Yeah, go ahead, try. As a hint, I'm gonna put the two faces there, the happy face and the frown face, right? Yeah, frown face. Look at the mouth of a frown face. Look at the mouth of a happy face. Trace the graph and then see, right, what is concave up, concave down. It's tricky, I agree, right? It's harder to visualize than visualizing the trend. Main link, yeah, you made my day, main link. You got it. Yeah, very good. Yeah, so here clearly, when you travel along the curve, right, all the way up to here, this resembles the mouth of a frown face. So concave down, right? Concave down, but where? From 0 here to -infinity, right? So -infinity, 0 is the interval for this graph being concave down. Similarly, if you continue from here, it's tricky, yeah, all the way here, this resembles the mouth of a happy face. So concave up, where? On concave up over this interval from 0 to the right to +infinity, right? Great. But not only that, this point should be a local max, and this point in the bottom should be a local mean, right? Locally, they are maximum and minimum respectively, right? So when you look through, this is the one you have to choose, right? Local minimum at x equal 3, local minimum, right? Which is this here at x equal 3. Local maximum at x equal -3, correct here, right? There. And not only that, concave down from -infinity to concave up from 0 to infinity, right? Correct here from 0 to infinity, and concave down from -infinity up to 0, right? Up to 0. You follow, guys? Great. Okay, so now let's talk about. Yeah, go ahead.
I'm sorry, just a question.
Yeah, go ahead.
So we end one of the concavities when it hits the y-axis. Consider that
very good question. Excellent question, right? We are ending here at the y-axis, right? Yeah, because this is kind of a basic question, but this point is important. Very good that you mentioned. This point is going to be called the inflection point soon. But for now, just try to look at the y-axis, right? There will be a point there where the curvature will change, it will be clear where the curvature changes. In this case, when it hit the y-axis, right here and here. Very good way to catch it, right? Yeah, but later when it's not so clear, I will show you how to catch it using the second derivative. So it will be precise, the location, right?
Right,
Okay.
but why did you put 0 though?
Oh, because notice up to here, if you zoom in, right, where this ends? Doesn't it end right there at 0? It's not like let me show you. Yeah, it's here where it ends, right? At this level, right? Down here. First, this point has first coordinate 0, right? First coordinate 0. The second coordinate, I don't know. But the first coordinate definitely 0, right? Yeah, so that's why we gotta be careful there. Let's put it back there. Yeah, so but now don't worry about the location, because I will give you a method to find it precisely. Soon, okay? Soon I will give you a method to find it precisely, right? Yeah, so local minimum, local maximum. Yeah, this is 3 negative. Yeah, this point we will be able with the second derivative exactly pinpoint this as 0, something, right? But for now, just visually you have to do it here, right?
Right, but the graph doesn't hit 0. Like it hits below it, doesn't it? Like if you look at it zoomed in, doesn't it hit below 0?
No, yeah, it hits below 0, but still
Right.
the first coordinate, the first coordinate of this orange point, this orange point has 2 coordinates, right? 0, something, right? I don't know what that something is, right? Suppose the graph does this, it will be the same answer. Do you follow? The same answer, because as long as it hits here, right? As long as it hits on the y-axis, that's the separation, right? And this is when you're gonna, yeah, so very good. Yeah, for now, this leave it there, but we will find it precisely. Okay, great. So now I want to talk about how to find this change of concavity point, right? But precisely. So we have no doubt of where it is. It's called testing for concavity. And also then we will find it as a inflection point, right? First, let's do the testing for concavity. How to know precisely where the function is concave up, where the function is concave down? Well, in order to test for concavity, we said, right, second derivative positive, concave up, second derivative negative, concave down, right? So we are going to find then our second derivative now, right? Not the first, but the second now. So, but in order to go to the second derivative, I have to go through the first derivative, right? So let's take the first derivative, is this, it's 12x plus 9, right? That's the first derivative. Let's take now the second derivative. Second derivative should be 6x minus 12, right? And now let's set this equal to 0, right? Set our second derivative equal to 0 to see where the second derivative is positive, where the second derivative is negative, right? So 6x minus 12 will be equal to 0. Moving this 12 to the right side, 6x equal 12, leading to x, 6 into 12, 2, right? 2. I got this special point. It's not really a critical point because it's, if you want to call it critical point, you should say the critical point of the derivative function, right? Not the critical point of the original function, but it's a special point. And this special point should be placed on the number line, just like we did before with the first derivative, right? But now we are using the second derivative. So you place this here. Now, this special point will separate your number line into 2 regions, right? 2 sub-intervals. And the idea now is to figure out the sign of the second derivative, right? The second derivative. For that, I'm gonna use test points. Anyone could give me a good test point for the right side of 2?
3.
3, right? Yeah, it's kind of natural to choose a good test point, right? And now this test point must be evaluated into our second derivative, which is this, right? 6 times 3 minus 12. 6 times 3 is 18 minus 12, 6, right? Turn out to be positive, right? Positive. So it means that all this region will be positive. Great. Now, anyone could tell me a good test point for the left side of 2?
0.
One.
Zero win the winner, I would say. Zero, nothing is easier than evaluate compared to zero, right? F of zero, second derivative. No, you just put zero, this disappears, right? This is just minus 12, right? Clear. Yeah, second derivative all the way to zero, minus 12, negative, right? Negative less than zero. So all this negative. So concave up here from 2 to infinity, concave down from negative infinity to 2, right? As simple as that, guys. So conclusion, the concavity report, right, will say concave up on 2, infinity, right? Here, concave up, like happy mouth of a happy face, right? And here, the mouth of the frown face. Concave down on negative infinity up to 2, right? Up to 2. Excellent, right? That's it. So this is the first thing we have to kind of master. How to figure out when the function is concave up, when it's concave down, right? It will help us to identify the shape of the graph. So I want you to try, just like I did that exercise, this one. Figure out where this function is concave up and where is concave down. Hint, get the second derivative, right? Remember, the second derivative controls the concavity, right? And set it equal to 0, right? And then find those special points, right? The critical points of the derivative. This is the formal way to look at it. So set second derivative equal to 0, get your critical points of the derivative function, right? And then set them on the number line. And according to the signs of the second derivative, you should be able to identify where that function is concave up and where the function is concave down.
Professor, can you show that graph, like a rough sketch of that graph?
The previous one?
Yeah, like
one.
because
Sure.
I don't know, I feel like the 0 and the 2, that's like the x-axis, right? You're showing, yeah, I don't know.
You know this graph, and verify that the concavity. Sure. Let's do it. The original graph was this, right? Yeah. Some graphs, if the numbers are friendly, you will see the whole thing in our grapher, right? But some others not, but you can kind of change the scale, right, with the mouse, and then you will get it. But let's take a look at this. It's good that you always check, verify, right, the concavity. This really makes it look at this. Look, the scale is very bad, right? But we will try to make it fit. Yeah, so maybe you can drag this down, right? Yeah, you see, this is a good place to see it. Yeah, we said ourselves, right, that this the concavity was changing. What value was there? At
2. It was 2 was our middle, I think. I don't remember.
Yeah, the point in the middle,
Yeah.
2, right? Consistent with this, right? This is 2. You see, right here the concavity changes at 2. You see, look, 2.72 right there.
Right.
By holding them out, yeah. You see, 2.02, yeah.
Yeah.
So it's a change of concavity. You see, right? Concave down on the left and concave up on the right, right? Makes sense?
Okay. Yeah. So that
Okay.
first coordinate means what value of x is our concavity change and concavity
Yeah,
change.
at what value of x, where is it happening, the change of concavity, right?
Okay,
The other
right.
value is the actual value that we will use there to next in the exam. Very good, very good, right?
But we didn't
So-
stop necessarily at the y-axis, right?
Oh, not in this one, right? Not in this one,
Right,
but here
we
you
didn't
can see
stop,
that we
yeah.
were able to see it, right? Two,
Mhm,
right?
yeah.
There, this is the point, exactly. Look, 2,32, right? Yeah, great,
Mhm.
great, excellent.
Okay.
Excellent.
Okay, thank you, Professor.
Question. Yeah, so let's go back to the exercise. Yeah, and probably we can do this together so I can show you more forms. Let's do it together, okay? So in question number 2, if you find the derivative, right? Remember, in order to get the second derivative, you have to go through the first derivative, right? So let's start with the first derivative. Someone figured this out, I think. Deep, yeah, number 2. Deep, yeah, you made my day. Excellent, Deep, excellent work, excellent. Yeah, you got it, excellent. Yeah, the first derivative should be 18x squared plus 2, right? Second derivative for concavity, remember, we need a second derivative, 36x, right? Plus this 0. And then we have to set our second derivative equal to 0. So bottom line, 36x equals 0, which leads to x equal 0, right? X equals 0. Believe it or not, guys, this is the special point. This is the critical point of the derivative function, right? And that's the one that we have to set on the number line. Miguel, yeah, also Miguel, very good, Miguel. Excellent, good work, guys, good work. So excellent work. So 0 in the middle here, right? This 0 is going to separate our number line into two sub intervals, right? So anyone could give me a good test point for the right side of 0? What would be a good one?
Right
Positive
side,
1, right? 1, excellent, right? 1. You don't need to go far, yes? 1 is good. Now, this one must be evaluated into your second derivative, right? Here. But this second derivative is so easy to evaluate. Look, it's just 36 times x. So this is 36 positive, right? Positive. So it means that all this region has a positive second derivative, sign of second derivative, right? Q second. Great. This means concave up, right? Yeah. Now let's investigate what happens here. And a good test point for the left side of 0. Anyone could give me a good test point?
-1.
-1, right? It's good always to consider symmetry, right? If 1 was the best for this guy, -1 should be good for this. -1 evaluated here, so easy to evaluate. 36 times -1 minus 36, which happens to be negative, right? Negative. Yeah. So it means that it's going to be, as a conclusion, right? The concavity report, look, concave up on from 0 to infinity, right? Concave down on from negative infinity to 0, right? Yeah, very good, guys. Excellent. And then this makes the answer, this guy, right? Excellent. Great. Okay, guys, now I have to talk to you about what separates concave down from concave up, right? That's the special point that we even saw in the graph, right? This is a special point that separates two different types of concavity. Mathematicians have given it a name. It's called the inflection point, okay? And formally speaking, mathematicians define this inflection point as follows. If f is continuous all in one piece, right? And if f changes concavity at A, this point is called the inflection point. So remember, that point that we're looking for before was 2,32, I think. That's called inflection point because it separates the concavity, the two different types of concavity. In this case, it's separating concave up from concave down. How do you know, Professor, concave up from concave down? This is clearly happy face, right? The mouth of a happy face. And this is clearly the mouth of a frown face, right? Yeah, but it could be that the graph was like this, right? Frown face first and then happy face. As long as there is a change of concavity, then you got yourself what is called an inflection point. And I'm going to show you how to find it using second derivatives. Now, here, this picture is very interesting because it's showing you the concavity together with a change of the trend, right? Look here, first decreasing, derivative negative, reaches derivative 0, then increasing, derivative positive. But throughout all this region, concavity up, right? Concave up, slope increasing. Over here, concave down, right? And increasing here first, derivative 0, and then decreasing. Notice something important. When you draw that tangent line right at the inflection point, notice what happens. Part of the curve will be above the tangent line, but the other part of the curve will be below the tangent line, right? Remember, when the graph is dominant, concave up, when the tangent line is dominant, concave down, right? Yeah, very good. So Now we are going to combine both first derivative and second derivative, and we will be able to describe completely the graph, right? We will find out about the trend, the concavity, where the trend changes, where the concavity changes. This is, now let's talk about this second derivative test, which is a test that you will have on the side, okay? Because I'm gonna show you a strategy to use just the first derivative to do basically everything, and the second derivative just to locate the inflection point. But this second derivative test could be on the side to check directly if a point is associated to maximum or minimum by using the second derivative. Look, suppose you know that the derivative is 0 at some point, meaning you are talking about maybe the top of a mountain or the floor of a valley, right? But you don't know. Well, then one thing you can do, according to mathematicians, is you take the second derivative. If the second derivative is positive, it means that it's concave up, right? Second derivative positive, concave up, happy face. So therefore, if it's concave up, clearly it has a local minimum, right? Look here, local minimum. See? Now, if on the other hand, you evaluate the second derivative at that point, right? And your second derivative is negative, then it will resemble a frown face, right? A frown face. But the frown face, the mouth of the frown face clearly tells you that you are dealing with a local max, right? Local max. Now, if the second derivative is 0, neither positive nor negative, the second derivative 0, then reserve your judgment, because remember, I told you, right, that it could be that this is the case, right? So neither increasing nor decreasing, right? So probably there is a change of concavity there, right? So just reserve your judgment. An example of how to use the second derivative test to catch local maximum, local minimums here. In this example, just consider this function and suppose that you found the critical points already. The critical points are 3 and -2, okay? They both satisfy the derivative evaluated at this point 0. What this is saying is use the second derivative test, this test, right, to determine whether f has a local maximum or a local minimum. Local maximum or a local minimum, right? Using the second derivative test. Well, then for the second derivative test, I need the second derivative, right? So quickly take your first derivative, which is going to be 3x squared minus, look, this number 2 comes down, cancels this 2 in the bottom, and this is just minus 3x, right? One less on the top, and the derivative of this part, 18, right? 18. This is the first derivative. But I need the second derivative because I'm dealing with the second derivative test, right? So second derivative will be 2 times 3, 6x, minus derivative of 3x, just 3, right? Now, I need to do a couple of evaluations, right? The second derivative test says, right, if you evaluate your critical points on your second derivative, right, depending on this being positive or negative, you will know if you're dealing with local maximum or local minimum, right? Let's evaluate the derivative, the second derivative at x equal 3. This is the second derivative, right? So let's do that. 6 times 3 minus 3. 6 times 3 is 18. 18 minus 3 is 15, right? This 15 is greater than 0. Second derivative positive. What does it mean? Then the graph at that x value should resemble a happy face, a mouth or a happy face to be precise, right? So if I'm having this, clearly this guy should lead to a local minimum, right? Local minimum, because the second derivative positive. Similarly, in order to find out if this other critical point is associated with the local maximum or local minimum, I can use the second derivative test. So evaluate this -2 at your second derivative. 6 times -2 minus 3. This is -12 minus 3, -15, right? -15, which turns out to be negative now. But if it is negative, second derivative negative, remember, resembles the mouth of a frown face. Right? So clearly I'm talking about a local max, right? Local max. Very good. Local mean, local max. Right? So as simple as that, guys, you can use the second derivative to check that, right? It's a nice test. But now let's put everything together, right? Let's try to use this method and figure out where is the change of concavity, right? So this deals with this type of exercises, right? So let me do number 2 to show you. And then I will ask you to number 3, okay? On number 2, they say, right, here instructions, use the concavity theorem to determine where the given function is concave up and where it is concave down. Also find all inflection points, okay? All right, so suppose we have this function q of x equal 3x cubed plus 2x plus 8, and I am going to figure out where it is concave up, where it is concave down, and also I will figure out where the concavity changes and therefore find the inflection points, okay? So let's start by taking the first derivative. That is 9x squared plus 12, right? Plus 2, sorry. So now next I should compute the second derivative, which is going to be 18x, right? Now I am supposed to set the second derivative equal to 0, right? To see where the change of concavity will happen. So 18x equals 0. From there, dividing by 18 both sides, I get that x equals 0 is that special point where the concavity changes. So what I do next is this. I set this x equals 0 here in the middle. That will separate the number line to 2 sub-intervals. I need to use test points, right, to figure out the signs of the second derivative. Sine of q double prime of x. For here, I'm going to choose out of convenience the number 1 for test point, right? And I'm going to evaluate my second derivative at 1. What is that? This is just 18 times 1, which leads to 18, right? 18. And I can similarly consider here -1 as my test point and find out what is the second derivative of -1. 18 times -1 is going to be -18. So this will be negative, right? Negative here, positive here. So it just means that the concavity is positive or concave up from 0 to infinity and concave down from -infinity to 0, right? But not only that, right? Not only that, look, the report here says concave down on -infinity, 0, concave up on 0, infinity, right? And not only that, there is change of concavity, right? Since there is change of concavity from concave down to concave up, there is change of concavity, then we can say that we got ourselves an inflection point, right? There is change of concavity, then 0, its partner, right, via the function will be an inflection point, right? But what is the partner of 0 via this function? Well, I evaluate my original function, right? Be careful with that. It's the original function that must be evaluated. And I quickly realized that the partner of 0 is 8, right? 8. So since there is change of concavity, then 0, its partner 8 is an inflection point, right? Very good. So therefore, the answer for number 2 must be this one, right? This guy. Yeah, Ma, you raise your hand.
Yeah, Professor, I just wanted to clear a few things that I'm just like thinking.
Yeah,
So
sure.
when we set the derivative, like the first derivative of a function to 0, we are finding the critical points.
Yes.
When we
Yes.
set the second derivative to 0, is that us finding the inflection point, like one coordinate?
When you set the second derivative equal to 0, then you are finding the critical points of the derivative function, right? Of the derivative function. Yeah, but you're right. Now, are they all inflection points? Not always. Only when there is change of concavity. For example, here from concave down to concave up, there will be a change of concavity. Then we got ourselves inflection point. But sometimes the sign of the concavity of the second derivative will not change. So we cannot say that is an inflection point, right? Yeah. But
right.
Most of the time it will lead to an inflection point. Yes.
Okay. And when you say when we set the second derivative to 0, we are finding the critical points of the second derivative, you said?
No. When you set the second derivative equal to 0, you are trying to see where the second derivative is 0, right? So then you are finding the critical points of the first derivative. Of the first derivative function, right? Yeah, it's like yeah, right? It's like a little bit tricky. Yeah. You can call them critical points, but I don't want you to confuse them with the critical points of the original function, right? They are the critical points of the derivative function. Yes.
Right. So they're different from our original function.
Yes.
Our graph is different than what our original function is, basically.
Yeah, the graph of the function is different than the graph of the derivative, right? They have different graphs. Yes.
Right.
Yeah.
Okay.
Yeah, very good, Maria, to untangle of this. Yeah, guys. So now maybe you can try number 3. Let's try number 3, which is a little bit tricky. Let's do it together probably, but try to do this at least as much as you can. And then I will do one with degree 4. Okay. Yeah. Try to do this. The function is t of t. Instead of x, they are using t, but this is the function. And try to, since they are dealing with concavity, find second derivative and set it equal to 0. Set the second derivative of this function equal to 0 and find those special points that just Ma mentioned, right? That are going to be the critical points of the derivative function, right? But those will allow us to figure out if there is an inflection point or not. Yeah, try that and find the special points. I see. Someone figure this out. Yeah, let's see number 3. Deep. Yeah, good job. Very good, Deep. Very good. Yeah, second derivative equal to 0. And then you should be good to go. Yeah, very good. Yeah. All right, let's do it together, guys, so I can show you one with polynomial of degree 4, okay? All right, so the idea is to find the second derivative because we are dealing with concavity, right? Remember, second derivative controls concavity. First derivative controls just the trend, right? Increasing or decreasing, but second derivative is needed. So let's find the first derivative, which is going to be 2 minus 3t squared. And right away, let's take the second derivative now. Second derivative is going to be what? Negative 6t, right? Negative 6t. Next, we are supposed to set our second derivative equal to 0, right? And solve for t, right? Solve for t. So if we do that, negative 60 equal to 0 leads to, once you divide both sides of this equation by negative 6, to t equals 0, right? Aha. This is a critical point, but of this function, not of the original, right? You see, Ma? It's the critical point of the derivative function, right? Or you can call it just a special point. Yeah, you can just call it a special point, right? Yeah, very good, very good. Now, this is the one that you have to consider on the number line here, right? 0. And you have to here figure out the sign of the second derivative, t second, right, of t. This determines two regions. Let's do the work on the right of 0 first. For that, I'm going to choose a test point 1. So if I evaluate my second derivative at 1, not hard to do that because look, the second derivative is very simple. This is this. I am going to get -6, which is a negative number, right? Negative number. So this means that all this region has second derivative negative. For the region on the left, subinterval on the left, I'm going to choose this red color. I'm going to use test point -1. -1 as my test point, okay? So the second derivative evaluated at -1 is -6 times -1, +6, right? Greater than 0, +6. So positive all this. So concave up here, concave down here, right? Let's just write it quickly. Concave up, and this one concave down. Concave down. At x equals 0, there is a change of concavity, right? Concavity changes. Then this point 0 together with its partner, what is its partner is what you get when you substitute 0 into the original function, right? Which is this. It's just 0, right? So it means that 0, 0 is an inflection point. Inflection point. And this allows you to say that the answer should be this one, right? For number 3. Yes. Excellent, excellent, right? Concave up from, notice here is negative infinity, right? Negative infinity to 0, concave down, concave up, sorry, negative infinity to 0 here, and concave down from 0 to infinity, right? 0 to infinity here, over here, this concave down. And 0, 0 is the inflection point, okay? We got it. Now, let me show you quickly this one. This is the longest it could get, right? But I will show you for you to see that it's not that difficult. Let's say they give you a polynomial of degree 4, and they ask you to figure out the concavity and where the inflection points are. All right, so quickly you get the derivative, right? First derivative is this 4 comes down, multiplying a quarter is just 1. So x to the third here minus 3x squared, derivative is 0, right? This is the first derivative, but since we are dealing with concavity, we need the second derivative. Second derivative will be 3x squared minus 6x, right? Now next, you set your second derivative, right? Second derivative equal to 0 and solve for x, right? To find those special points that could lead us to inflection point, right? Yeah. So we set the second derivative equal to 0. Factor out 3, the greatest common factor, together with x, right? Greatest common factor for x squared and x. 3x into 3x squared, 3 cancels with 3, it's just x, minus, 3x into 6x, 3 into 6 is 2, right? So end up with this. Divide both sides by 3, you get rid of this constant, right? So don't worry about this. So it's just x times x minus 2 equal to 0, which is going to lead to this, x equals 0 or x minus 2 equals 0. So here I have a special point, and I have another special point. If you want to call them critical points, call them critical points of the derivative function, right? But these two special points will allow us to examine where the function is concave up, where is concave down, right? Set 0 and 2 on your number line. This will separate this into 3 regions, negative infinity here, positive infinity here. Let's use test points, right? To figure out the signs of the second derivative, right? G double prime. A good test point here could be 3, right? Let's use it. So second derivative evaluated at 3 is what? Well, I have to use my second derivative, which is this guy, right? Second derivative is this guy. So there, look, 3 squared is 9. 9 times 3, 27. 27, 6 times 3, 18. 27 minus 18, I think it's 17, right? Yeah. Yeah, 17, I think. Yeah, so this is gonna be positive. I think it's not. Let's do the computation, right? So let's make sure. The sign is all that matters, but evaluating, right? 3 squared is 27. This one, right? So 27, yeah, squared minus 6 times 3. 9. Yeah, it's 9, right? Good. So positive, right? Positive. So first one, positive. 9, positive. So all this positive. Now for this, I'm gonna take the number 1 as my test point. I evaluate my second derivative of 1. This one we can do it on our minds, right? This is 1 times 3, 3, minus 6 times 1, 6. 3 minus 6, negative 3, right? Negative. So all this negative. Second derivative. Concave down, right? And then this last part, let's choose another color. Let me use negative 1 as my test point. Second derivative negative 1. Negative 1 squared is 1 times 3, 3. Negative 1 times negative 6 is positive 6. 6 plus 3, 9, right? So positive. So positive here, my second derivative. Concave up here, concave down here, concave up here, right? Notice there is a change on the concavity, right? On the concavity. So I'm gonna write here, since there is change of concavity, then we got ourselves an inflection point here at x equals 0 and another inflection point here at x equals 2 because again, change of concavity, right? So since there is change of concavity at x equals 0 and at x equals 2, then this will lead to 2 inflection points, right? Then 0 together with its partner via the original function or via the original function right here. Look, don't forget. G evaluated at 0 here, look, is a quarter of 0 to the 4 minus 0 cubed plus 14. This is just 14, right? So 0, 14 is our first inflection point. And the other inflection point will be 2, its partner via the function, right? The original function. So now I have to evaluate this function at 2. This will be a quarter, 2 to the 4 minus 2 to the third plus 14. 2 to the 4 power is 16. 4 into 16, 4. 4. This is 2 to the third by 8. 4 minus 8 minus 4. Minus 4 plus 14. 10, right? 10. Yeah, you can do this with a calculator, guys, in case you cannot do it in your mind. So 2, 10 will be the second inflection point, right? These two guys are inflection points. In general, cubic functions, they show just one inflection point because they look like chairs, right? But functions of degree 4, in general, right? Not always though, they show 2 inflection points, right? Just kind of for you to have a reference there. Yeah, and if you graph this function, you will see those inflection points when you zoom in, right, around this x value 0 and 2, right, for this particular function. Yeah, so therefore the answer should be this one, right? Concave up on negative infinity to 0. This U means union together with 2, 0, right? 2, infinity, sorry, concave up here and here, and concave down on 0 between 0 and 2, right? Inflection point 0, 14 here and 2, 10 here, right? Someone is writing something on the chat. Deep. Yeah, you got it, Deep. Very good, very good. Excellent. Yeah, very good, guys. So now with this, we have finished with the material, right? Up to